For the rest of this presentation, we're going to focus on the most common type of roundness instrument, the rotating workpiece instrument. In this image, the main components of the measuring system can be seen, and we'll look at some more of those in more detail in the next few slides. First of the main components is the stylus. The stylus is often interchangeable. So for example, just here, the stylus can be inserted into the stylus holder and removed, changed with a different stylus. And the stylus can often be altered in its angle in relation to the axis of the gauge, and you can see the mechanism here for doing that. The stylus force is also adjustable. Difficult to see on this image, but there is a stylus force adjustment knob just here on the side of the gauge at that point. The stylus tip is an essential element, forming the one point of contact with the surface under test. The size, shape of the material of the tip will all affect the results. Typically, the tip is a polished sphere of a suitable hard material such as ruby, silicon nitride or tungsten carbide. The diameter of the sphere is usually of the order of millimeters. The gauge, which is this part here, is responsible for converting the small movements of the stylus into an electrical signal that can be processed and recorded by the data acquisition system. Frequently, the gauge has, as I've mentioned before, some mechanism for adjusting both the stylus force and the angle at which the stylus is presented to the surface. Moving on to the spindle, this is obviously vital to the operation of this type of roundness measurement instrument. Various types of spindles are used depending on the application and the load requirements. Hydrostatic bearings use either air or oil and are very common these days. For the measurement of roundness, the spindle or spindle drive needs to provide some reference as to its position relative to a 0-degree reference point. In a rotating workpiece instrument, the spindle will typically be fitted with a centering and leveling stage to aid alignment of the component axis to the rotational axis of the spindle. The silver top on this one is the centering leveling stage. This is one of two centering knobs, and this is one of two leveling knobs that are provided. So there are some other main components which we're not going to look at in any detail. And for example, there is the arm, the column and the framework, and they provide the support to the gauge and can provide additional capabilities or features to the instrument. For example, linear axes that are motorized or provide straightness datums may increase the flexibility of the instrument or extend its capability to other measurement types such as straightness. The framework will usually incorporate some form of anti-vibration mounting to isolate the instrument from external noise such as floorborne vibration. And the electronics really contains the data acquisition system and some form of computer for reporting purposes. So once the component has been loaded for measurement, the basic approach to the measurement of roundness follows a pattern similar to the one that's outlined here. Firstly, the stylus is brought into contact with the component, and then the component is aligned to the axis of rotation. The stylus is then moved to the required feature, and the component is measured by rotating the spindle. Stylus tip deviations are recorded as a function of spindle position, and the resulting dataset is then analysed to produce the result. With an automated instrument, the entire sequence could potentially be initiated by a single touch of a button. For a manual system, a skilled operator is required to perform the alignment and then initiate the measurement sequence.